Physics chapter 30 theory video 4. We are going to learn about computerized axial tomography. So this is what we refer to as the CAT scan or CT scan. Now X-rays have many limitations. Mainly the main limitation is it gives us a two-dimensional shadow image. So the bones and organs we can't actually identify how it is going to be. Now in this particular picture you can't see the difference between what is at the back, the bone that is at the back and bone that is at the front, where it is going to be and where is the heart. So any of these things you can't figure out. So to see what is going on inside the patient, in 1971, Jeffrey Hounsfield and some colleagues of his developed a machine called computerized axial tomography scanner, CAT scanner or CT scanner. So here what happens is the patient would lie on a bed, and around him there is a vertical ring of X-ray tubes, detectors. So this X-ray tube would rotate around the ring, and the patient will be exposed to a kind of a fan-shaped beam of X-rays from everywhere, from all around. Then there are detectors opposite the tube, and they will get this electronic signal to a computer. The computer softwares will develop whatever the data that comes into a 3D image of the patient. The interior would be made it into a kind of a slice kind of a thing. So then slices through the patient's body can be viewed through the computer screen. So that is what happens in this CAT scan. So when this spiral path allows us to get a clearer inside view of the body. Now here it is shown the a child's head has been scanned. So then you can see you can see here the eye sockets are scanned. So that means you can clearly see the if there is anything wrong with the eyes also. So these soft tissues and everything can be seen through that. This is X-ray technology is being used to get a 3D image. The reason tomos means in Greek, it means slice. So because slices are observed through the patient, we see this computerized axial tomography. The reason why we say obviously computerized is because we use computers to make this, computer programs are used to make use of the data that comes. So the CT scans are better alternatives sometimes because they produce 3D images, so we can see different relationships between different tissues. And also when there are tissues with similar densities, there is attenuation coefficients. When they are similar, still they can distinguish between them. Then if there is a tumor, there is a cancerous tissue that has developed inside the body, this CT scan will show its position, shape and size. Everything can be diagnosed with this. And then targeted treatment, that is when radiotherapy is performed, including X-rays or gamma rays, we can precisely attack the tumor without harming any other tissue. However, still CT scan involve X-rays, so there is a risk, but this risk is very minimal. Now, for example, a single CT scan would be similar to the 1/3 dose that we receive from background radiation. Or when we go on long haul flights, when we go up in the sky, there are radiation that we get exposed to, more radiation. So that is similar to 4 long haul flights. But still we need to know about the dangers, because if a woman is pregnant or if there are other health concerns, that might be important to know those things. So I suggest that you do question 8 and 9, but before that, let's write down a note. Write down computerized axial tomography within brackets CT scan or CAT scan. To overcome the limitations of X-ray, which gives only a 2D shadow image, CAT scanner has been developed where a patient who lie on a vertical who lie on a horizontal bed placed in a vertical ring of X-ray detectors is scanned while the X-ray tube rotates. This results in a fan-shaped beam of X-rays from all directions, which should be detected by the opposite detectors and sent to a computer. Computer softwares develop a 3D image of the patient, which gives an image of the slices of the patient's body. It can precisely give position, shape, size of a tissue, as well as while giving a 3D relationship between tissues, it distinguishes between tissues with quite similar densities, within brackets attenuation coefficients. Leave a line and write, however, because CT scans use X-rays, there is a risk of exposure. Right, now moving on to ultrasound, using ultrasound in medicine. Now we know that ultrasound is a very important use. It has many important uses. Mainly this is used to check the condition of a baby in the womb. Usually there is no harmful side effects to this, and or at least we have not discovered that much of harm of this particular use. Usually it is considered to be very safe. For example, there are other uses for this as well. For example, heart problems can be detected. Um, Now, when thinking about Doppler effect and related to the blood flow, when blood flows, we have an understanding about Doppler effect and how blood flows through the heart. That is also using Doppler effect we can figure out if there is any hindrance to blood flow. So that is also something that we can figure out using ultrasound scans. Then also gallstones or kidney stones, they can also be detected using ultrasound. This is actually quite similar to using echo sounding and echolocation by bats and ships to find out whether with the depth of the sea, and also if there are any shoals of fish. So the ultrasound is directed to patient's body, and when they get reflected by different boundaries, then we can figure out what is there in it by creating an image. So using this um, reflected sound waves, we can create an image. So obviously this image is created by a computer, so that would be taken onto a screen. So ultrasound means above the frequency that we can hear, that is beyond upper limit of our frequency. So our frequencies that we usually hear is 20 to 20, above 20,000, 20 to 20,000 hertz. So if it is above 20,000 hertz, that is 20 kilohertz, we don't hear that. So now we usually use megahertz range of range uh, to uh, to use this, to create the ultrasound image. We use megahertz range of frequencies. Because they are longitudinal waves, they need a material medium to pass through. So if there is a vacuum, they can't pass through it. So now you would be, if you have been thinking carefully, then you would understand, if the medium changes or if the densities change, it would get reflected in different ways. The speed of sound depends on the material. So in air it is 330 meters per second. In solid materials it is higher. In body tissue it is 1500 meters per second. It is very high. So we use V equals F lambda. Then if you use 2 megahertz ultrasound wave in tissues, then lambda is going to be V upon F, and you calculate it to be 1 millimeter. So that means 2 megahertz ultrasound waves will be able to will be able to give us and distinguish detailed features if the dimensions of a particular thing inside our body is in the order of 1 millimeter. So if you want to see smaller features, then you will have to use a higher frequency waves having shorter wavelengths. So because higher frequency waves are absorbed more strongly, more intense beam must be used. So that is another. So that is actually a practical application that has to be, the machines need to be produced in that manner. So ultrasound is also produced by vibrating a source like audible sound. So the frequency of the source should be the same as the frequency of the wave that produces. So ultrasonic waves are produced by a electrical voltage, varying electrical voltage in a transducer. So the same device will act as a detector. So transducer is any device that changes energy from one form to another. That is something that you have learned earlier. Now in the middle of this transducer is a piezoelectrical crystal such as quartz. This crystal is actually acts as one of the most important applications here. When a voltage is given across it in one direction, it will shrink slightly. When it is reversed, it expands slightly. So when you alternate the voltage with the frequency that allow the crystal to expand and contract, then what happens is this will this width will change by a certain margin, right? So now in a good piezoelectrical substance, the strain would be about 0.1%. That means its width would change by about 1 part in 1,000. So here, when you apply voltage in one direction, it goes, it induces a strain, then applies a stress. So this mechanism is known as piezoelectric effect. This is not something that you need to go into detail of, but you will have to understand what this actually is caused, how it is caused. So what happens is an alternating voltage is applied across the crystal. When so that actually starts to vibrate because of this stress that is created on it. So that pulse or that vibration sends a pulse of ultrasound into the patient's body. So that receives an extended pulse of reflected ultrasound waves. So that is what that is exactly what we use to detect the sound that is coming from the interior. I think it would be best if we write down a note on this. Write down using ultrasound. An image can be created by sending ultrasound waves through human body and detecting what is reflected. Ultrasound means above human hearing capacity, that is above 20 kilohertz. In ultrasound medical applications, usually megahertz ranges are used. Because sound waves are longitudinal waves, they only pass through a medium, and in solid materials it has a higher speed. For body tissue, usually it is 1500 meters per second. If we use a 2 megahertz ultrasound wave, we will be able to distinguish features whose dimensions are of the order 1 millimeter. Write this equation down. Lambda equals V upon F. 1500 over 2 into 10 to the power 6, which is equal to 7.5 into 10 to the power minus 4 meters, which is equal to 1 millimeter, which is more or less equal to 1 millimeter. Ultrasound pulses are created using a transducer, which itself works as the detector. A piezoelectric crystal such as quartz is used to generate the pulse. When a voltage is applied in one direction, it shrinks slightly. When the voltage is reversed, it expands slightly. So alternating the voltage with a frequency f causes the crystal to vibrate in the same frequency f. Leave a line, put a star and write down. We say that the voltage induces a strain in the crystal. now we have to detect this ultrasound that comes. So we know that we heard that the transducer itself will act as the detector. So this is possible because the piezoelectric effect works in reverse as well. So that means when a varying stress applied to the crystal produces a varying EMF. That means when the sound returns, it creates a it actually it makes the crystal to vibrate. That generates a voltage across the crystal. So we have to maximize this effect. When to maximize the effect, the waves must match the resonant frequency of the crystal. So we have to optimize these things. So the optimum size of the crystal is half the wavelength of the ultrasound wave. So whatever the wavelength that we send, half of that is used as the crystal that we are going to use. So in the 30.14 image in that picture, you will see the construction of a piezoelectric ultrasound transducer. So there are these features. The crystal is usually now it is made of polyvinylidene difluoride. Earlier, quartz and lead zirconate titanate were used. So that is no longer used. Now mainly it is most of the time it is polyvinylidene difluoride. Then there is an outer case which protects the crystal and also it supports it. There is an acoustic window at the bottom. That is a good transmitter of ultrasound. Then there is a block of damping material, usually epoxy resin. So that would stop the crystal vibrating when a pulse has been generated. The reason why it is needed is when the vibrating when the crystal when after the pulse has been sent, the incoming or the reflected ultrasound, when it reaches back to the transducer, it should not be vibrating. If it was vibrating, that is going to be a problem, because then it cannot detect it. So after sending it, it should be damped. The vibration should be damped and allowed it to respond or to detect what is incoming. Write down a note. Ultrasound is produced by a vibrating source. The vibrating frequency of the source is similar to the frequency of the ultrasound it produces. In ultrasonic waves, a varying electrical voltage in a transducer produces this pulse. The same device acts as a detector. At the heart of the transducer is a piezoelectric crystal such as quartz, which expands slightly when a voltage is applied in one direction and shrink and when it is My apologies, I said when the voltage is applied across in one direction, it shrinks slightly, and when the voltage is reversed, it expands slightly. This vibration creates the pulse, and it will be reflected by different muscle tissues. When the sound wave is reflected, it would be detected by the same piezoelectric crystal, which produces an EMF across the crystal. Leave a line and write, the optimum size of the crystal is half the wavelength of the ultrasound wave, lambda upon 2. Many developments have been done to maximize the accuracy of ultrasound scanners. In modern day machines, crystal is made of polyvinyl iodine difluoride, within brackets earlier quartz and lead zirconate titanate were used. There is an outer case which supports and protects the crystal. At the base, there is an acoustic window made of a good transmitter of ultrasound. Behind the block, there is a damping material, usually epoxy resin, which helps to stop the crystal vibrating after the pulse has been generated. Put a dash and write, so that the crystal is not vibrating when the incoming reflected ultrasound waves reach the transducer. I hope you understood. If you have any questions, please ask. If not, please do question number 10 and 11.